Okay, so now let's continue our review of differential geometry. So this is review of differential geometry. So continuation. So so let's assume that the connection on a tangent bundle, for example. So, okay, so now if you fix a coordinate chart, you see, so this is like M, right? And you have a small patch, and you have a concrete homeomorphism or diffeomorphism between these and some subset of Rn now. This is called the coordinate chart, right? So you base up the coordinate chart on your manifold M. Now, if Tm, if you look at Tm over U, so if the manifold, for example, is n-dimensional, then this is isomorphic as a vector bundle. It's going to be isomorphic to U cross Rn. Right, so this is a vector bundle isomorphism, right? And then there is a frame on U. So I denoted it by di, which is also another notation is ddxi. So this is coordinates that we have here to come to Rn. And these guys have, so I between n and 1. So these guys have two interpretations. We work with both interpretations. One interpretation is that if we think of, so this is basic vector fields on U, right? Basic vector fields. U. So these vector fields, if you think of vector fields as derivations, then this is just di of f equal to d dxi of f. It's just partial derivatives, right? But there is another interpretation which is directly related to this isomorphism. So if you look at this isomorphism, basically, EI is a constant field which picks the ith. So here, if you imagine you have this like E1, E2, En standard basis for Rn. And in this case, in this interpretation, di is just going to be well, it's just I'm going to write it as EI, but what really means is a section of this. So this is basically, so DI, some point like X is equal to X, and the second component, which is going to pick a direction in Rn, which is one of those EIs, is going to be 0, 0, 1, okay. Either interpretation is used, and we are using this most often. So in particular, if you use this first interpretation immediately shows that the commutator of di and dj's is equal to 0, because second partials commute, right? So this, I mean, this is because d2 dxi dxj is equal to d2 dxj dxi. So this most often is used in calculations. If you use this sort of frame, But you're not bound to use this frame, so you can use general frames, and in that case, the bracket of two frame vectors is not zero, so you get something. So this is something to bear in mind. And the second concept I want to talk about is Christoffel symbols. It's not very essential right now, but eventually you may see this. So Christoffel symbols, so what are they? So because we have fixed this, so notation is this by definition. We denote this kind of operation di. So covariant derivative with respect to di, it's convenient not to put this vector field over there and just call it di, right? So then if you think about it, then you can just write dij, right? So if you take these frames and covariant differentiated with respect to dj or vice versa, then you're going to get some sums of these basis frames again, right? So this is going to be something like gamma I, j, k, and then, okay, so I should be careful with my notation. I'm going to put d here, dk is going to be k here, and ij is going to be ij here. Yes, okay. So these are basis frame vectors. We are summing over them, and I and j gives you these two components. So my notation is consistent. ji. Oh yeah. So this is this we have to be consistent with rest of the words. So this is ij. You read from down up, and then left right. It matches like this. So. It's just a convention, but it's important to observe the convention. So these n-cubed functions on U, which is base of the coordinate chart, and I'm using coordinate chart because I'm using dk now, are called Christoffel symbols. So these are Christoffel symbols of this connection in this coordinate chart. So this is important. Sometime we will use it later on. Okay.
What is this gamma ijk?
Oh, gamma ijk. So that's the notation, because these are just some coefficients of this. Because this is a vector, we expanded in this basis, right? So we just expand this vector in this basis, and you get these numbers. But these numbers changes from point to point. Because this is not just a vector, it's a vector field after all, right? So you move from point to point to point. So these numbers change from point to point to point. So these are functions on you.
Okay. Yeah.
Okay. Yeah, that's good. Yeah, very good. Any other questions? Okay. So this is good. So these are Christoffel symbols, but these are really n-cubed functions on you. So now let me also introduce Riemannian metric, the idea of Riemannian metric. So that's a very simple idea. Again, I mean, what you do, so you pick an inner product on each tangent space in such a way that these inner products move in a smooth way, right? So for each tangent space, Tm at x, you pick an inner product over there. So like this. So this is a positive definite inner product. Inner product on on TMX for all x in M. So this is a very general idea of Riemannian metric, but we want to work with the smooth metrics. We don't want to have metrics that have jumps in a crazy way from point to point. And imposing a smoothness condition on this is very easy. I will tell you how to impose a smoothness conditions. So once you have that, then you can get some functions on U again, like this. So these are GIJs. This is inner product of dI and dj. So this is the tangent space. You have these two vectors, dI and dj. At that point, you take the inner products and you let the point change. So you get a function on U. So these are functions on U. And of course, these functions, there is nothing invariant about these functions. If you change the coordinate, you get on the neighborhood of x a different set of functions, but that's okay. So this Gij, we can also think of it as a matrix n by n, matrix. Now, as I said, how you can impose a smoothness condition? A smoothness condition is very easy. So smoothness of this Riemannian metric, it means the following. For any two smooth vector fields, the inner product of them, which is a function on M, should be smooth. It's a very simple natural definition. Once you put in first slot, second slot, x and y, for any smooth x and y, you should get a smooth function. Then this is the definition of smooth. Alternatively, you can say that it's a smooth if in some coordinate Gijs are smooth. This is equivalent to Gijs are smooth functions on U for all coordinate chart U. So defining a smoothness is not a problem. So some notation, you may see notation for Riemannian metric in a chart written like ds squared equal to sum Gij dxi dxj. Sometimes even people don't put this. Okay, so that's okay. Just put Gij dxi tensor dxj. These are all same thing. That's these are they refer to the same thing. So summation is over I and j, obviously. Okay. So, but this is a very, very useful notation, incredibly powerful notation. This was introduced by Riemann himself. So, examples of Riemannian metric, so flat metric on Rn. Of course, ds squared, you can just say in this case, is sum of dxi squared, right? Over I. So, of course, in this case, Gij is just delta ij. Or so this is this matrix. If you want to write it as a matrix, which is sometimes not a good idea, but you can just think of it as a matrix. It's just this. So example 2, we can think of Poincare metric, for example. There are many metrics, of course. So in this case, your manifold is H upper half plane. And ds2 is equal to dx squared plus dy squared over y squared. You see, this is not flat a priori. I mean, it's not of this form. So the metric in this case, Gij, is this 2 by 2 matrix, 1 over 2, 0, 0, 1 over y2. Sorry. Okay, that's of that form. Okay. So this is another example of a metric, point a metric. Okay.
So for the smoothness of the Riemannian metric, the equivalent of saying Gij smooth function on U, is it for some Gij? And then what is
Yeah,
so
right. Yes. No, yeah, that's a very good question. If you can show it for some Gij, then you can show it. You can show that for all Gij, for all coordinates, it's going to be a smooth. Yeah, for all coordinates, they are equivalent. Yes, because if you have Gij in one chart, you can have Gij in any intersecting chart by some change of variables which are smooth. So that doesn't affect the smoothness after that. Yeah. Very good question. Actually, this is a good idea to prove it even. It's a simple exercise to prove it. So I should try to give some exercises here just for review problems.
And then just to make sure that it's for all coordinate charts on them. For
all coordinate charts, or for a set of coordinate charts that covers M.
Okay.
You know what I mean? If you just have one set of coordinates that covers M, and you have this checked, then you have checked it for all coordinate charts. So that makes things easier, right?
And another question. So ds there, is it an element in some algebra?
ds?
Ds, is it ds squared?
Oh, ds squared? No, this is notation.
But then you have the tensor there, so I thought it would be in some algebra, an element in some algebra.
You don't have to think of it as an element of algebra right now. It's really ds squared. You can think of ds as you see, the reason I write the reason they write this squared is that then ds is equal to square root of Gij dxi dxj. Then when you want to calculate length, I don't need it right now, but then this is like ds. So this is like integral a to b square root of sum Gij dxi dxj. So this is the formula for calculating length of curve on a Riemannian manifold. So it's kind of suggestive notation, right? You have infinitesimal of length, and you just integrate it, you get the length. Okay, so that's the reason we have s squared. Okay. So now, I need one more concept, well, several concepts today for the review. So another one is compatibility. So definition, let Mg be a Riemannian manifold. A connection nabla on Tm is called compatible with G So we say that this connection is compatible with the Riemannian metric if nabla, I would say x, so my notation, I want to be consistent. Yeah, no, y I put here, yxz inner product plus y nabla of zx is equal to x times inner product of z and y, or y and z, it doesn't matter. Y and z, yes. So this is the definition. I mean, in that case, we just say that nabla is compatible with the metric. So in this form, it's not very easy to motivate this definition. This is a definition that is very good, has an algebraic meaning, very nice algebraic expression, but geometrically it's not clear what it means. So basically, this is, it means, so I don't need this interpretation, but I just tell you, it's equivalent to parallel transport defined by nabla preserves metric. So let me just quickly, I don't need this and I'm not going to use it, but just let me just say, the parallel transport is this. Once you have nabla, you get this operation of parallel transport, which is the following. If you have a curve on your manifold, and if you have a vector field, I mean, just a vector at one point, you can take this vector and move it on the curve in such a way that it remains parallel to itself. Now, defining parallel, it takes some work, but that's okay. So when you do parallel transport, you come back to the same point. So the parallel transport, say x, you come back to same point, but you don't necessarily come back to the same vector. You may get a different vector. So I call it x prime. So x is turned into x prime. So this parallel transform is an operation from Tmx to itself. And of course, it depends on the choice of the curve as well. So it's not just x, it's also the curve that you go around and come back to this point. Basically, this condition, we can show that is equivalent to saying that this map preserves metric. So it's metric preserving. In other words, is an element of the orthogonal group of the tangent space at that point. So this is a very geometric object. It's an isometry of tangent space for all curves and for all x. But this is good enough for us right now. Okay. So
that G, does it denote the collection of inner product or
this D?
G, the MG Riemannian manifold?
Sorry, this D you mean here?
The definition. So MG, let MG be a Riemannian manifold.
Or yeah, okay.
So what is the G?
Oh, G is the Riemannian metric. Yes. Riemannian metric.
So it's a collection of inner products for each x.
Yes. So I mean, I define GIJs, but then collectively it's convenient to call it G, but it doesn't matter. And in this thing, I just use this bracket notation, not G. Yeah, I could have said that. Yeah. Okay. Good. Any other questions about notation? So now I can define the Levi-Civita connection. So definition. Actually, I can give the theorem. This is Levi-Civita theorem. For any Riemannian manifold, and G, there exists a unique compatible symmetric connection. Nabla. So this nabla is called the Levi-Civita connection. So this nabla is called Levi-Civita connection. So I defined already compatible, so I have to define for you what symmetric means. Symmetric means the following. Symmetric is the same as torsion-free, and it means the following, that nabla xy minus nabla yx minus bracket of x and y equal to 0 for all x and y smooth vector fields. Okay. So this is my notation. These are smooth sections of tangent bundle, which is a smooth vector field, right? So this is the definition of being symmetric. If you impose two conditions, namely this condition and that condition, then there exists a unique. So it has two statements. First of all, it exists. Second of all, it's unique. Nabla, which is this property. This is called the Levi-Civita connection of the Riemannian manifold. So now we have a way of producing from Mg a connection nabla. So if we use, and then of course here we can just use take curvature of nabla, curvature operator as I defined last lecture. So it follows that actually Riemannian manifolds, you can talk about curvature of Riemannian manifolds by this. First, you construct the Levi-Civita connection, then you take the curvature operator of the Levi-Civita connection, and this is called the curvature operator of the Riemannian manifold. Okay. Now, let me tell you something.
I'm not sure, but in the symmetry, is the x and the y supposed to be the other way around in the nablas?
Oh, here?
Well, either there or in the nablas.
Nabla xy minus nabla yx minus bracket of x and y? Or you think it should be bracket of y and x?
Yeah, or switch around the nabla coefficients.
Right. Oh, yeah, you're right. Absolutely. How did you know this?
Because I think it's supposed to look similar to the curvature. It's supposed to be the same way around that you get it in the curvature.
Well, I'm very impressed. Excellent, Tori. That's great. So yeah, indeed. Although I still don't understand what it should be, but my note actually is exactly what you said. Because if we have it the other way around, then you're going to pick a wrong sign here and everything collapses. Indeed, that's very sensitive. Of the xy minus bracket of x and y equal to 0. Yeah, I'm not, so I have to do the calculation, see why this is the correct one. I still don't see why this should be the correct one, except by analogy that you mentioned, but, oh, very good. Excellent. So, but now let me give you an exercise about this no matter what. This is kind of interesting anyhow. So the exercise or whatever review is this. in general, show that T of x and y equal to nabla y x minus nabla x y minus commutator of x and y is C infinity of m linear in x and y. This is quite surprising, right? Because as we saw, this is not nabla, this is not C infinity of m linear in y. It is in x, but it's not in y. And this one is in x again, but not again. This is in x, but not in y. And this is not C infinity of m linear in any of x and y. But if you do this combination, it's C infinity of m linear. This is called torsion tensor. Tensor of this manifold with a connection. You don't need Riemannian metric for this, of course. We just define it. So what is this torsion? Then torsion goes from C infinity of Tm cross C infinity of Tm to C infinity of Tm. Right? Because I mean, a vector field, the result is a vector field. So this is a map. Now we are saying that this is actually C infinity of m linear in both coordinates. So that's why we are allowed to call it a tensor, but don't worry about the exact meaning of tensor at this stage. That's good. So this is nice exercise. So we are saying that the torsion tensor should vanish. That's why it's called torsion free. Torsion free means the torsion is zero. So that's it. So this is a theorem. The proof is not difficult, but there is even a formula. So I can just maybe give you the formula for the Chivita connection. For nabla Levi-Civita, as we discussed, it's enough just to give the Christopher symbols of a connection. You have to go through the proof, but that's at the end you derive that gamma L JK equal to 1/2 sum GLR over R, and then dk GRJ mine plus dj GRK minus dr GJK. Absolutely no reason to remember this formula. So it's just the existence of this. Okay. Any questions? So we discussed Levi-Civita thing. So now let me give you another exercise, just a simple exercise. Compute gamma ijk for gray metric ds2, I mean dx squared plus dy squared over y squared. So a priori you have like 2 to 8 of these, but many of them are 0, and you will just find what gamma ijk's are for this metric. So that's not a difficult exercise. Okay. Very good. Now, another thing we need is a bit of, so let me just do a bit of review of differential forms. Okay, so recall that we had this Tm was this tangent bundle. I also told you that if you have a bundle, basically all operations of linear algebra that are canonically defined and are defined independently of choice of basis, these are kind of categorical operations or canonical operations. On linear algebra, on vector spaces, all these operations can be lifted to the class of vector bundles, to the world of vector bundles. They have analogs in vector bundles. In particular, the dual space, so this is called dual vector bundle, T star. I mean, it should really be called Tm star, but nobody writes it like that. Everybody writes it as T star of that. So this is the dual vector bundle. Okay, so this is called cotangent bundle. Cotangent bundle. Now, let's look at basis or frames for this. Remember, we discussed frames for Tm. So this was like di, which was d dxi, right? So this was a local frame for Tm. So from linear algebra, if you have a basis for V, this gives you basis F1, F2, Fn, which is dual basis for the dual space V star, right? And remember, these are defined as Fi j is equal to delta ij, right? I mean, it makes sense because for each I, you have defined its value on all basis vectors. So this is so this Fi belongs to V star. And remember, V star was harm of V and R. It's a dual space. So if V is your space of vectors, this V star sometimes is called a space of covectors, but that's an older notation. Anyway, so we have this, right? So now what you can do, you can take this definition from linear algebra, pure linear algebra, and do it point to point. Okay, so we have this basis point from point to point, this one, and we repeat that construction point to point. So let dxi, I from 1 to n, this is dual frame. So what are dxi's? Dxi's are smooth sections of this, T star of m, of course, on a chart, because we cannot go beyond the chart. We have no way, no right to discuss something globally on the manifold because there are no, in general, there are no global coordinates, right? So you just have to specify a chart and do things in that chart, and then, yeah. So this satisfies this property that dxi, ddxj is equal to delta ij. I mean, exactly like here. Okay, so this notation and this notation are very, very fundamental notations for in differential geometry. So vector fields x, we can always locally write it as xi ddxi. Or we can just write it as some xi di. Locally, right? Locally, we can always write a vector field like this, but these xi's are the smooth functions on U, right? And we can do the same for the smooth sections of the cotangent bundle. So dually, for omega belonging to C infinity of T star of n, we can certainly write omega as, again, locally, omega can be written as sum omega I. So I have to put it down, omega I dxi. So omega i's are smooth functions again on U. So these guys are called one forms. So one form now is any element just on smooth section of T star of n. Just a one form. So now you know one form. You might wonder what the heck. I mean, this is exactly looks like a vector field. You're just changing the notation. You might tell me you're just playing with notations. This is not. I mean, it's the same thing. No, they are not the same thing. They are globally very, very different. When globalized, I mean, you look at over the whole manifold, you will see that things are very, very different. So, but this is right now, locally, they look like the same except for change of notation, of course. Okay. Now, there is a notation for one forms. C infinity of T star of n. This is just too much to work to write. This is denoted by omega 1 of n. So this is a space of one forms. Of course, I say smooth one forms, right? Because we're dealing with smooth one forms. And remember, we had also our smooth of functions. And now I can, functions. Now I can define a map D from C infinity of m to omega 1 of m. So takes a function f, surprise, surprise, it's mapped to df, right? So what is df? df is called differential of f, and the easiest way to define df is to use coordinates like that. And in fact, df is equal to locally, df is equal to sum df dxi, I from 1 to n. You see, these are these functions omega i's now. Okay, so these are omega i's. But they are of a very, very particular type because this one forms is obtained from function by differentiating. So this D is called the Rham differential. Rham differential. Now, everything, of course, is in local coordinates, but you can check that the definition is independent of choice of local coordinates. In a suitable sense, if you change local coordinates, this is fine. you can say maybe this is like the gradient, but it's not gradient because the result of gradient was a vector field. The result of D is not a vector field; is a one form. This is very, very important. Eventually, you will realize this is very important.
I have a question about the thing. So there is DXI, they are smooth section of T, the dual bundle of the
tangent bundle, yes.
I was just thinking why the dual frame is a smooth section of the thing.
Well, I mean, originally the thing itself is a smooth, and this is also a smooth because in that coordinate is just the one. It's constant one. If you just consider this in that coordinate, its component is just one. Yeah, so because component of di is one also. One is a constant function, so it's a smooth on U. Yeah. So yes, that's a smooth and deserved. Okay. So now I think it's a good time to take a break and we come back soon. Right. So now recall from linear algebra, from V we go to wedge 2 of V, which is V wedge V. This is V tensor V divided by some subspace S, where S is subspace generated by the set of X tensor X belonging to V. That's one definition, for example, of this exterior part. In a similar way, we can also define wedge 3 of V, wedge 4 of V, and so on. Right? So this way you just take you take V tensor V and divide it by some suitable thing such that if any two coincide, then this is going to be 0, and so on. So this idea of basic idea of linear algebra, we just take it now to vector bundles and apply is to bundle E, which is T star of M. Okay, so then we get these bundles, wedge 2 of T star of M, wedge 3 of T star of M, and so on. Of course, in this case, you notice immediately that wedge P of V is equal to 0 if P is bigger than dimension of V. It's very easy. By choosing a basis here, you can check, for example, here also you can check that this is 0 if P is bigger than dimension of V. And okay, so this stops somewhere at wedge N of T star of M, is the top one, which is N is dimension of M. Okay, now we are interested in the smooth sections of this thing. So remember, we called omega 1 M to be a smooth sections of T star M, right? Now, by the same token, we just denote the infinity of wedge 2 of T star of M. And this is called the space of two forms. And omega P of M in general P forms. Okay. Up to omega N, and which is top forms. So these are top forms. So that's good. But I mean, abstractly, we cannot do much except we just gain some abstract understanding, but then again, locally we have to go to coordinates and working coordinates. And actually, when you go to coordinates, things becomes very, very simple to work, extremely simple to work with. So let me show you how this happens. So in local charts, so well, I mean, we have this. Okay, so this is a local frame belongs to omega 1 of m restricted to u. I mean, okay, so omega 1 of belongs to omega 1 of u. You see, I'm using one forms on u because I mean this is the manifold, and there is this chart u, and just focusing on one forms on u. Then there is this frame, and any one form omega can be written as sum, as I did here, omega I dxi. So this is what we already did last lecture, right? Now, what we can do, we can just construct a basis for, I mean, a frame for omega 2 of u. A frame like dxi wedge dxj, I less than j for omega 2 of u. So how many of these vectors are there? Well, I mean, this is just n choose 2, right? Because I less than j, the number of 2 element subsets of this. So the rules here is that dxi wedge dxj is equal to -1 dxj wedge dxi. In particular, dxi wedge dxi actually is equal to 0, because if I and j are, this is for all I and j now, I say, not just I less than j, and then this is the case. So you may complain and tell me that, hey, you did not even define what this wedge dxi wedge dxj is. But you can take this as the notation for a basis here. So I mean, just can. So for the moment, let's take this for a notation. And following these rules. If I want to be very formal, I can take a basis here, a basis there. I mean, in this case, by the way, we are working with dual basis. And then we just take dxi tensor dxj, and we look at its image under the projection map from V tensor V into the quotient. We call this dxi wedge dxj. I mean, that's the notation. So this is a definition, actually, it's not even a notation. So it's mapped into this under the canonical projection from V tensor V to V tensor V divided by S, which is wedge 2 of V. Okay, so now if we use this basis or frame, elements of omega 2 then can be written as. So, I mean, there are many different ways to do these things. I mean, this is not the only way. So you can just, for omega can be written as sum omega ij dxi wedge dxj I less than j, or you can just say over I and j, it doesn't matter. Okay, so this is a 2 form locally. And you can also define a 3 form. I mean, we already defined it, but you can just drive the expression omega ijk dxi wedge dxj wedge dxk. Now, these guys are just smooth functions, right? This is as usual. I mean, these are basis elements. Okay. So now we can extend D to this thing as well. So we already have d from omega 0 of m, which is another notation for C infinity of m, by the way, just to be consistent with other forms, to omega 1 of m. So it's the map that sends f to df as we define, right? Now we want to extend it. So d from omega 1m to omega 2m. How do you extend this? Well, definition is very simple. D of sum omega I dxi is equal to sum d omega I dxi. I mean, veg dxi. Okay. Well, these are locally functions. You can take differential of functions, veg it with dxi, and you get a two form. Right? Now, there is an issue here. The issue is you have to make sure this is well defined. So this is an exercise, nice exercise in very, very basic differential geometry. You show that D is well defined. In other words, if you go to another basis, another frame or basis, then you do this, you get the same two forms. That's something one has to do at least once in your life to make sure you understand. But you see, I mean, working with this thing, with the notation is extremely simple. I mean, this notation is very, very efficient. That's what I'm saying. Extremely efficient. So you can extend by the same reasoning then D to higher forms. You can go from omega pm to omega p plus 1m, right? So D of sum omega I1 IP dx I1 H dx IP, we just define sum, you apply D to create the one form, then multiply by the others. I1 dx IP, and you have to put wedge here, but even these wedges, I mean, if you work enough with these notations, you notice that you don't even need to put the wedge signs. I mean, it's understood that this is an exterior product. So okay, so far what we did, we have got this now. Up to omega n, and then go to Z. Oh, okay, so we are here up to here. Now, a very interesting result is the following. The result is that, so this is a lemma, is that D composed with D is equal to 0, i.e., I mean, this is a complex of vector spaces, so well, it doesn't matter. I don't want to introduce more terminology here, just for sake of terminology. So this is a calculation. Let me just do it in the case of see what is involved. Proof. This is a consequence of what kind of fact of calculus you think will imply this? What fact of calculus is involved here, you think? In the proof.
The partial differentials commute.
That's right. It's a consequence of this thing that d2f dxi dxj is equal to d2f dxj dxi. It's amazing how many times we already use this. It's a very nice thing to know. So let me just check it on this level. Omega 0 and d omega 1 and d omega 2m. Let's check this, that this is equal to 0. So what we have to do, we have to take d of f, right? What is that? That's d of sum omega I dxi, dxi. Right? But then again, this is equal to sum d of omega I dxi over I. So this is equal to, but we know how to calculate d, right? So d is equal to so this d is equal to sum now over j d dxj omega I dxj wedge dxi. This is just this one. Oh gosh. There's a mistake here. I should have written here. This is, this is just df dxi. This is not an arbitrary one form. It's a differential of a function. So it's of this form. So this is d of df. You didn't complain. I'm surprised. Maybe you noticed, but you're just too polite. That's good. df dxi dxi. So this is d dxj now, df dxi, dxj dash dxi. So the sum then, the total sum is equal to sum p2 f dxj dxi dxj wedge dxi. Okay, now I'm claiming that this is equal to 0 basis of two facts. One fact is this one, this coordinate set. So this is equal to 0 using this. But that's not enough. That's not enough. We have to use the fact that dxi wedge dxj, dxj wedge dxi is equal to minus dxi wedge dxj. So that this is a sum. But if you order, then you just get for ijji switch, but you pick up a sign, and then as a result, those guys cancel and everything cancels. So the fact that d squared is 0 is a consequence of two things. We chose to work with antisymmetric objects, and also the fact that it is well defined is a result of the fact that we are working with covectors or differential forms, not vector fields. That's important. And a consequence of the symmetry of second partials. These are all important, right? Okay, so now the exercise is, at least I want you to do it for this omega 1, d omega 2m, omega 3m. This also show that it's 0. This is a nice, when you're bored, sitting at home, just try to do that. This is useful. Okay, so that's one thing. Any questions?
I guess I'm just kind of curious as to, so when you have d squared is equal to 0, then that chain is a co-chain complex, a finite one. Is there something you can say about that? Or
Yes.
is there anything you can say about that in that way, or?
Sorry, can you speak louder?
I was just thinking if there is anything interesting you can say about the co-chain complex there.
Absolutely, yeah, no, exactly. That's absolutely that's coming. This is a co-chain complex, exactly. This the Rham complex. So by the way, yeah, okay. So now that you encourage me to talk about it even now, so that's very good. So this is called the Rham complex. So you see, this is amazing because we just have a smooth manifold, nothing else. We are not talking about metrics, connections, curvature, nothing. Just a smooth structure gave us this so far. This is the Rham complex. I mean, technically it's a co-chain complex, but that doesn't matter. It's a Rham complex. Okay, so as with any complex, what you can do, you can take cohomology of this complex. So its cohomology is the Rham cohomology. It's called the Rham cohomology. So what is it? I mean, the word cohomology is very simple in this case. What does it mean? So let me denote HP. The Rham of M by definition is equal to the kernel of this guy. I just write omega p to omega p plus 1 divided by image of b from omega p minus 1 to omega p. You see, the fact that d2 is equal to 0, it means that image is inside kernel. So this is really subspace of this. So these are called closed P forms. Yes, P forms divided by exact P forms. So these are closed P forms divided by exact P forms. And this is the Pete Rham cohomology of M. Okay, now one thing to know is Rham's theorem, which is actually needed. So Rham's theorem. If M, for example, is compact and oriented, I mean, compact, I mean, let me put it like this, closed, I mean, which means compact without boundary. And I may even need orientation. Yeah, let me put it like this, unoriented. There exists canonical isomorphisms. Between HP, the Rham of M, with H P singular of M with coefficients in R with dual. There's a canonical isomorphism between this space and the dual of singular cohomology with coefficients in R. In other words, i.e., there exists a natural pairing from HP to the Rham of M cross HP singular homology of M and R to R, which is non-degenerate. Exists a natural which is non-degenerate. And in fact, this is given by integration. So it's a very natural thing to do. You just integrate. So let me tell you how this works. I'm getting a little bit ahead of myself, but that's okay. So if you have a class here, and a class here, so a singular chain, is mapped to integral of omega over c. And the fact that this is well-defined, non-degenerate, and all these properties is a consequence of, it's a statement of the Rham's theorem. So that's one of the most beautiful theorems in differential topology, because it tells you that you can compute cohomology of your manifold with real coefficients, which is the dual of singular homology, from the Rham cohomology as well. That's a very nice exercise in this case. Okay. I will come back to this a little later. Now, one piece of structure that I want still, it is one piece of a structure is ring structure. I mean, really it means R algebra, really, that's what I mean. More than just a ring, is an R algebra structure on omega dx sum of omega p of n, p from 0 up to. You can multiply differential forms. So, I mean, this, and omega 1 and omega 2, the thing is defined by omega 1 wedge omega 2. This is uniquely defined using the rules. I mean, just dx1 wedge, say dxi1, dxit, for example, for a p4, and dxj1 wedge dxj is mapped to, you just multiply and just put a wedge here, that's all. IP wedge dx j1 wedge dx jq. Of course, you may get 0 now because, for example, if you have something like dx1, and dx1, if you want to multiply these two, you go to dx1, wedge dx1, but I already told you that dx1 wedge dx1 is 0 by my rules of the way I define these p forms, or two forms in this case, right? So this is equal to 0. So, I mean, this is completely straightforward by defining it like that. Of course, if you want to be very, very careful, you have to make sure that this is, again, well defined, but this is just, that's just what it is. It's well defined. So, it gives us a ring structure here. And this ring structure has some nice properties. It's graded commutative. So first of all, wedge is graded commutative. Graded commutative means that, of course, omega 1 wedge omega 2 is equal to -1 to degree of omega 1, degree of omega 2, omega 2 wedge omega 1. And second of all, Now you have to worry about what is the meaning of this D with respect to the wedge product, how they behave with respect to each other. And in fact, there is a generalization of Leibniz rule of calculus. So Leibniz rule is true in this case, which is omega 1. So D of omega 1 wedge omega 2 is equal to D of omega 1 wedge omega 2 plus minus 1 to degree of omega 1 omega 1 wedge D omega 2. Okay. So this is an extension. So this follows from calculus rule dfg equal to df times g plus f times dg. I mean, this really follows from ddx of fg. I mean, so let me write it like this actually. So f prime, fg prime equal to f prime g plus fg prime. This implies this, and this implies that. So, and this is of course calculus, Leibniz, which is the mother of all Leibniz formulas, and this is the essence of all these things. They're all called Leibniz because of this. Okay, so one more concept, that's the idea of volume form. Any questions? Okay, so now let me just ask you to do this. That's the volume form. So now let us put a Riemannian metric on the manifold. Let the G, I mean, let me just write it like this, be a Riemannian metric on M. And let's assume that N is oriented. So M is not something like Mobius band, which doesn't have an orientation. It's oriented. It means it's orientable, and an orientation is fixed on M, right? If you have difficulty with orientation, just let me know. I will explain. But that's something from basic stuff. So now the volume form. This is actually rho denotes it by wall. There's also d wall. So define an element belonging to omega n of m, where n is equal to dimension of m. So there is no global definition, but we have to go into local coordinates. Is defined in local coordinates. Local chart by, so volume, the following n form is the square root of now a determinant of G. So maybe I can just say this is G. Determinant of G dx1 wedge dxn. So now in a local, oriented local chart. In any oriented local chart by this expression. So this is a very, very, very important expression. At least you can see that locally this is an n form, right? Locally is an n form. Now, what you have to do in order to make sure that you have defined some object of global interest is to check that this is actually independent of choice of basis. check. So exercise again. Wall is independent of choice of basis. So in this case, actually, it has a very clear meaning what we want to do, right? We want to show that, i.e., square root of determinant of g dx1 wedge dxn is equal to square root of determinant of g tilde dy1 wedge dyn if yi is equal to if yi is equal to yi of x1 xn I between n. So I'm abusing the notation a little bit because I denote the function and the value of the function by the same notation, but this is a standard way to do it. Because otherwise, in differential geometry, you get just crazy amount of formulas, which is not good. So everyone understand that when you write yi of x1, xn, it means that this is new coordinate, these are old coordinate, and these are functions. So so yi serves two purposes at the same time. It's very nice. So what is g tilde? So what is g? Okay, what is the determinant of g? Well, the determinant of g is really the determinant of just matrix Gijx. Because I told you that if you have a coordinate like that, then you can just take Gij's and then take its determinant, square root of the determinant. And this is positive because the metric is positive definite, right? So, now, what is the determinant of g tilde? It's really determinant of Gij in coordinate y. If you write Gij in coordinate y, I didn't have a better notation. I called it g tilde, but maybe there is a better notation you can think. That's okay. So basically, what it means that you take this in new coordinate, compute it, you get exactly the same n4 in that coordinate, provided that these coordinates are oriented. This is a very nice exercise. It will, you just need to know something about, just determinant, basically, and the exterior products, because we put here p by 1, you calculate these differentials, and there is a lot of nice things happen. So, basically, this follows from definition of determinant as alternating sums of products of column elements. So that's that. That's the thing. Another thing that we need is from basic geometry, we need the idea of, again, using metric, I want to define inner products on all these bundles. Okay. So let me just tell you. So again, linear algebra. So imagine you have an inner product on V. Then you can get inner product on V star, which is on V and R. So this is a purely linear algebra question. I ask you, I have an inner product, positive definite, for example, it doesn't matter much, on my finite dimensional vector space V. Can you define an inner product on the dual space? I ask you the question. What is the answer?
I guess if V is finite dimensional, you can do that?
Yes. So how?
defined by basis. If you choose a basis E1 to En for V, then you have E1 star to En star, and then how do you define it? I guess.
No, that's a good line. Yes.
Eij star, Ei star, the tensor product of Ei star and Ej star should be delta Ij. That I guess would be how I would want to define it.
Yeah.
And it's same as the original space already.
Yeah. Yeah. And you make sure that the basis that you choose for the first one is an orthonormal basis.
Oh yeah.
Because if you don't use orthonormal basis, you haven't used the metric at all, right?
Okay.
So okay. Yeah, so yeah, indeed what we do is that pick an orthonormal basis. But there are zillions of orthonormal bases for V, so E1, En. And then you go to dual basis, as we did in general. I mean, this has nothing to do with the metric, this is stage now, second stage. One more basis. And then you say that, okay, this is an orthonormal basis for this metric. Declare, I'm saying that declare Fi as orthonormal basis for the metric in this star. I mean, you just say that, yes, the metric on V star is such that Fi, Fj, if you calculate this thing in V star, this is equal to delta Ij. This is possible. Now, of course, the problem is you have to show that, again, this is independent of choice of orthonormal basis. So you have to make sure that you can do this, right? So there's a little bit of problem here. You have to make sure. So that's exercise again, simple but important. Check this is well defined. Because you can choose zillions of different orthonormal bases. Why you are going to get the same inner product this way? There will be something, some orthogonal group stuff or something, orthogonal matrices appears. I mean, orthogonal matrices I'm teaching my 1600 first year students this year. So, okay, very good. So that's that. Now, inner product. On Tm we had, right? So we got this one. So this was the Riemannian metric, right? I mean, this Riemannian metric. Basically, this gave us this guy, right? For any x. So now we use this idea to equip the dual space with, or cotangent space with inner product. Get cotangent space. Okay, so you define it this way. Now here's a very nice exercise. So remember so the idea is that I want you to check that dxi, dxj, inner product in T star mx. What do you think is the value of these two basis vectors in the neo-inner product on T star? Remember, the value of this guy is Gij. I mean, that's how we define Gij, right? That's how we define Gij. So in particular, these Ti, Dj's are not orthonormal bases. because they come from coordinate charts. They don't come from the metric. This is just from coordinate chart. And coordinate charts can be crazy. Doesn't they? I mean, the tangent vectors to coordinate things doesn't have to be orthogonal to each other. So this is in general not delta ij. But what is the value of this guy now? If you follow this rule. Yeah, so this is a very important point. This is actually equal to Gij, which is Gij is equal to G inverse J. So this is the metric matrix G equal to Gij. You invert it, and you just declare these down indices to be your up indices here, and this is it. So this has to be proved. Of course, this is not obvious, right? So I want you to prove it. It's a very nice thing and very, very important. We use it. So the dual basis dxi's are not orthonormal. As di's, they are not orthonormal, but we know exactly how they behave. This is like Gij, this is Gij. So what does that mean? It means that essentially, if the frames on the tangent bundle, the inner product is large, the dual's inner product is very, very small. Basically, it becomes a small. It's a duality, right? It's a duality. If on the tangent space, your basis vectors are quite large in length or inner product, in the cotangent space, the dual vectors are very, very small. This is very important. Okay, so that's one thing. So now I can use this inner product to define inner product on wedge P. I mean, I'll just finish in 2 minutes. So wedge P of T star. And of course, wedge P of Tn. I mean, in this case, just we used this, I mean, at x for all x. So what is it? I mean, if you want to take, say, omega 1 wedge omega p, for example, p form, and then times eta 1 wedge eta p, by definition, this is equal to, I mean, this is a definition, this is equal to determinant of this matrix omega I product with eta j. So this is the thing. Now you have to make sure that this is positive definite inner product. So this is a positive definite. Now, why I can take inner product of omega I and eta j? Because these are one forms or point one forms, and I can use this construction to use the inner products point at each point, right? So I use that, and then this is the definition. So here you have to check that this is positive definite. That's the case. So now for the next lecture, so we are going to finish differential geometry next lecture, really, but I recommend, so read up Hodge star operator. Now you know everything. There is just one line to go to Hodge star from Rose booklet, that's in the references. So what is Hodge star? The Hodge star now is a map that goes from omega p of n to omega n minus p of n. Now I have to tell you what this, what are the conditions of n? M is an oriented. Orientation is important. Riemannian. Riemann structure is also important. Manifold. This is very, very important. So let me just define it. I mean, so it's a strange operation. You see, it's a strange operation because it takes a P form and sends it to n minus P form. So what is this operation? So it's defined for any, alpha belonging to omega P, for any beta belonging to omega P, the inner product of alpha and beta, which is defined by this thing. Pointwise, this is defined, right? This is equal to, okay, so this is alpha star, so I can put it like this, star of alpha, wedge, oh, okay, yeah. Star of alpha, wedge, beta, and here I put 1. Yes, so this is this uniquely defines this is star operation. Remember, this is an n form, right? This is an n form. This is a number. And now this is an n minus p form. This is a p form. So the product, the wedge product of n minus p form and p form is an n form. So these two n forms have to be the same for all choices of beta. In that case, now I want you to think about why it makes sense to define something by this formula. And then, okay, so then we'll use this to work with some. Just one more operation we need in order to work with Laplacians or manifolds. So, I mean, the real reason for this is that again, it goes back to linear algebra. Any question, by the way, before I finish? Okay, so I will explain this later on. That's okay. So this is the Hodge star. I mean, for example, the star of 1 is wall. Star of wall is 1. And yeah, you can just do some other things. Okay, guys, so I think we are done for now. So let me just